Euler method using Maxima Software. Consider a ordinary differential equation of the type dy by dx is equal to f of xy with initial condition, say y of x0 is equal to y0. Now we know that we cannot solve every differential equation analytically, so here we are going to apply numerical techniques to solve to obtain the approximate solution of the given differential equation using Euler method. So first we are going to develop here formula for Euler method. We can write this differential equation as dy is equal to f of xy dx. Now integrate this differential equation from y0 to y1. Dy is equal to the value of y0 at x is equal to x0 and value of y1 at x is equal to x1, therefore xy dx. Now the integration of dy is equal to y from y0 to y1, and on the interval for x0 less than or equal to x less than or equal to x1, we assume here f of xy is equal to f of x0 y0. Okay, and therefore take f of x0 y0 outside the integration, we get it is x0 to x1 dx. So now if we simplify this, it is equal to, if we put upper and lower limit, y1 minus y0 is equal to f of x0 y0, and the value of integration dx is equal to x from x0 to x1. Again, if we substitute the upper and lower limit, we get y1 minus y0 is equal to f of x0 y0 x1 minus x0. Now here we assume that h is equal to x1 minus x0. Okay, and therefore we get the formula for y1 is equal to y0 plus h f of x0 y0. So this is the formula to find the value of y1 at x is equal to x1. If we generalize this formula, similarly we can find the value of y2 as y2 is equal to y1 plus h f of x1 y1. If we apply the above technique again for x1 y1, we get the formula for, this is the formula for y2. In general, we can write this formula as yn plus 1 is equal to yn plus h f of xn yn. So this is the formula for to find or approximate solution at x is equal to xn. Okay, xn x of the given differential equation dy by dx is equal to f of xy. Now there is one more method to develop this formula, method number 2. Now given the differential equation dy by, I am writing again this, dy by dx is equal to f of xy with initial condition y of x0 is equal to y0. So we can write this as, okay, we know that at x is equal to x0, then the value of y is equal to y0. So if we and dy by dx, so derivative at point, so derivative at point x is equal to x0, that is, it gives us a slope. So slope is equal to, at x is equal to x0, which is equal to dy by dx at x is equal to x0, and which is equal to f of x0 y0. We know that an equation of tangent line, having equation of tangent line passing through, equation of tangent line passing through x0 y0 having slope m is y is equal to, that is y is equal to y0, that is, or in other terms we can write y minus y0 is equal to m times x minus x0. So here m is equal to f of x0 y0, so we write this as y is equal to y0 plus m, that is f of x0 y0 is equal to x minus x0. Again we know that if we okay, suppose this is the solution of the given differential equation. So say this is the solution of the given differential equation. Say this is the point, say x0, and this is a tangent line passing through at x0, and here is the point, say x1, y1, and here is an, at this point we get an exact solution, say x1, and say it is y of x1. This is what, as an exact solution. Y of x1 is what, exact solution. This is an approximate solution, but you can observe that this approximate solution is very close to exact solution, and therefore if we put here x is equal to x1, then we get y equal to y1. So y1 is equal to y0 plus f of x0 y0 x1 minus x0. Again we assume here x1 minus x0 is equal to h, and therefore the formula y1 is equal to y0 plus h f of x0 y0. So we apply this calculus technique, slope technique, to develop an Euler formula. Again you can apply the same logic for y2. That is, suppose here, but this is the, again this is what, a solution of the given differential equation, and this is what, a tangent line, sorry, so this is a tangent line at x0 y0 at x0, okay, and here is the point, say x1, and here is the point, say x2, okay. Then this is the y2 is an approximate solution, and here is the point, say x1. So solution is, I'm writing this solution here. Instead of this, consider this solution. Then you can observe x2, y of x2 is an exact solution. This is what, exact solution, and this is what, an approximate solution. So by using again same technique, we can write this as y2 is equal to y1 plus h f of x1 y1. In general we can develop a Euler formula as yn plus 1 is equal to yn plus h f of xn yn. Okay, so this is the Euler formula. Now next, now take a simple example. Say solve a differential equation dy by dx is equal to xy, first example, with initial condition y of 0 is equal to 1, and we want to find the value of y of 0.5, okay, with h is equal to 0.5, h is equal 0.5, not h is equal to 0.1. So the given, so if you compare this differential equation dy by dx is equal to xy with dy by dx is equal to f of xy, then we can easily obtain the value of f of xy is equal to x into y. X0, the initial condition x0 is 0, that is, this is the initial condition x0, y0 is equal to 1, h is equal to 0.1, and we want to determine what is the value of y at 0.5, that is, when x is equal to 0.5, we want to determine what is the value of y at this point. So now we are going by using Euler method. So the first we are going to obtain the value of y1. So the y1 is equal to y0 plus h f of x0 y0. So y1 is equal to y0 is 1 plus h is 0.1 f of x0 which is 0 and y0 is 1. So since f of xy is x into y, it is 1 plus 0.1 into 0 into 1. So 0 into 1 is 0, so the y1 is equal to 1. So the value of y1 is equal to 1, which is a value. So y1 gives y1 is equal to 1 at x1 is equal to x0 plus h. So the x0 is equal to x0 is 0 and h is 0.1, so x1 is equal to what? 0.1. so we obtain here y of 0.1 is equal to 1, y of 0.1. but we want to determine y of 0.5. We just find the we have just obtain the value of y of 0.1. okay, y of 0 is 1 is given and y of 0.1 is 1. We have just calculated by using Euler method. Now next for the second iteration x1 is equal to 0.1 and y1 is equal to 1. okay, again h is same 0.1 and f of xy is equal to x into y. So by using this information we can write the y2 as y1 plus h f of x1 y1. so y2 is equal to y1 is equal to 1 plus h is 0.1 into f of x1, that is 0.1, and y1 is equal to 1. so the f of xy is equal to x into y. so y2 is equal to 1 plus 0.1 into f of xy is equal to x into y. so it is 1 into 0.1. so 1 into 0.1 is 0.1, and if we multiply 0.1 into 0.1 we get 1 plus 0.01, and therefore the y2 is equal to 1.01. so y2 is equal to 1.01. this gives the value at x2, which is equal to x1 plus h, that is 0.1 plus 0.1 is equal to 0.2, and therefore y of 0.2 is equal to 1.01. so this is the value of y at x is equal to 0.2. we want to obtain the value of y of 0.5, and here we have calculated y of 0.2. so again for third iteration here x2 is equal to 0.2. okay, and then y2 is equal to 1.01 and h is equal to 0.1. so the value of x3 is what? x3 is x0 x2 plus h, so it is equal to x2 is 0.2 plus h, so it is 0.3, and y3 is equal to y2 plus h f of x2 y2 by using Euler formula. Euler formula. so y3 is equal to y2 is 1.01 plus h is equal to h is 0.1 and f of x2 is 0.2 and y2 is equal to 1.01, and therefore if we simplify this, f of xy is equal to, so y3 is equal to 1.01 plus 0.1 into this is 0.2 into 1.01. so if we simplify this, y3 is equal to 1.0302. so this is the value of y3 at x3. x3 is equal to 0.3. x3 is equal to 0.3. so y of 0.3 is equal to 1.0302. but and so next fourth iteration x4 is equal to x3 plus h, so it is equal to 0.4. x4 is 0.4, y4 is just, we have calculated the value of by using previous iteration, it is 1.0302, and h is equal to 0.1. so this is what y3. so y4 is equal to not x4, this is y3. y3. So y4 is equal to y3 plus h f of x3 y3. Just there is one x3 0.3, here it is x3 not x4. We are going to calculate this x3. Okay, so so I'm writing here x3 is x2 plus h 0.3. so and here okay, so this is the value of y3 at x3. So now the y4 is equal to y3 plus h time f of x3 y3. So y4 is equal to y3 is equal to 1.0302 plus h is 0.1 into f of x3 is 0.3. x3 is what? 0.3, and y3 is equal to 1.0302, and therefore y4 is equal to 1.0302 plus 0.1 into 0.3 into 1.0302. If we simplify this, then we get the value of y4 is equal to 1.0611. so this is the value of y at x is equal to x4 which is equal to 0.4. in other words, we can write this as y of 0.4 is equal to 1.0611. but since we want to determine y 0.5, so in the last iteration, the fifth iteration, here x4 is equal to 0.4 and y4 is equal to 1.0611. so y5 is equal to y4 plus h f of x4 y4. so it is equal to y5 is equal to y4 1.0611 plus h is equal to 0.1, f of x4 is 0.4, y4 is 1.0611. so if you substitute this, f of xy is what? X into y, it is given. so 1.0611 plus 0.1 into 0.4 into 1.0611, we get y5 is equal to 1.1036. So this is what the value of y5 at x5. so x5 is what? x5 is equal to x4 plus h, so it is 0.5. so here, hence, by using numerical techniques, that is by using Euler method, y of 0.5 is equal to 1.1036. This is again an approximate solution, not an exact solution. so we can also find an approximate solution. Okay, so the exact solution. This is what the given differential equation with initial condition, and here the y of 0.5 is 1.1036. now next, we can also find an exact solution by using analytical methods. now the given differential equation dy by dx is equal to x into y. so by using variable separable method, this is what? An analytical method. so variable separable method, we can write this differential equation as dy divided by y is equal to x dx. so now variable separated, therefore if we integrate, we get ln y is equal to x square by 2 plus c. so here, if we substitute the initial condition, what is the initial condition? Y of 0 is equal to 1, that is x is equal to 0, then y is equal to 1. so if we substitute this initial condition, we get the ln1 is equal to 0 by 2 plus c, and therefore c is equal to 0. from this we get c is 0, and therefore ln y is equal to x square by 2. From this we get y is equal to e raised to x square by 2. So this is what, and this is a solution we obtain by using analytical method. And here, so this is what y of x is equal to e raised to x square by 2. So here y of 0.5 is equal to e raised to 0.5 raised to 2 divided by 2. So if you solve this, we get 1.1331. so this is what an exact solution is equal to 1.1331. and what is an approximate solution? We obtain by using Euler method, and which is equal to 1.1036, this solution. But not every differential equation we can solve by using analytical method. So in that case, to obtain a solution, the numerical techniques are very important. That is, you can solve the differential equation by using Euler method, that is numerical techniques, which is not possible by using analytical method. Now we are going to apply the Maxima software to solve this Euler method. Now first we are going to write f of xy is equal to, here f of x y is equal to x into y. Here we want to assign here, so f of x y is equal to x into y. Now next, take x0 is equal to 0, then y0 is equal to 1, initial condition is 1, then h is equal to 0.1. so here you can observe, if we minimize this, the given f of xy is x into y, x0 is 0, y0 is 1, h is 0.1, and therefore y1 is equal to y0 plus h into f of x0 y0. So if we write this formula here, if we put here y1 is equal to 1, you can see here y1 is equal to 1 by using here the y1 is equal to what? 1. Y of 0.1 is 1. Now next the x1 is equal to x0 plus h. X1 is equal to what? X0 plus h. So x1 is 0.1, and y2 is equal to y1 plus h into f of x1 into y1 just from by using previous iteration, the value of y1 is what? 1, and x1 is what? If we add h in x0, we get x1. so y2 is y1 plus h f of x1 y1. So if we press enter, f of x1 y2, sorry, here I want to assign y1 plus x1, sorry, here we want to assign x1 is equal to, so now if you press here, if you press enter here, you can see here y2 is 1.01. you can check here y2 is what? 1.01. Similarly the x3 is equal to x3 naught y2. So next we want to determine x2 is equal to x1 not equal, want to assign, so x1 plus h. So x2 is 0.2, and y3 is equal to y2, want to assign it, so y2 plus h into f of x2 y2. If we press enter, you can see 1.0302. you can check here 1.0302. so this is what? y3. y3 is what 1.0302. Next next we want to determine the value of x3. X3 is equal to x2 plus h, x2 plus h, not equal, want to assign it, so you can check here x3 0.3, and therefore y4 is equal to y3 plus h into f of x3 y3. So if you press enter, it is 1.0611. you can check here, it is 1.0611. this is the value of y4 at x4. This is the value at x4. So what is x4 here? x4 is equal to x3 plus h. So x4 is what? 0.4. Now next, if you want to calculate the y5 is equal to y4 plus h into f of x4 y4. You can check, the answer is 1.1035, and here also it is 1.1036. so 1.1036, which is same as 1.1035. if we round up the given number to 4 decimal places, we get 1.1036. You can also solve this differential equation directly by using inbuilt function ODE2. So for that, if we assume here the equation is equal to, if you want to solve directly, so if you write here equation is equal to the equation is equal to the given differential equation is dy by dx is equal to, the given differential equation is dy by dx. So it is the command diff xy is equal to x into y. So if you press enter, you can see here dy by dx, sorry, not xy, it is yx. Differentiate y with respect to x, so dy by dx is equal to x into y. Now we want to solve this equation, so I am writing here the solution is equal to okay, ODE2 equation eqn xy in the variable of xy, and you can see here ODE2 not proper differential equation, yx maybe yx. Okay, you can check here y is equal to c time e raised to x square by 2. Now we want to put here initial condition. So solution, I am writing here solution 1, which gives us at initial condition. So initial condition for to put initial condition, write IC1 of solution x is equal to 0 and y is equal to 1. So if you put this initial condition, we get y is equal to x e raised to x square by 2. You can check here, if we put initial condition, if you substitute here, we obtain y is equal to what? E raised to x square by 2, because c is what? 0. So here similarly in maxima, we e raised to y is equal to e raised to x square by 2. And finally we want answer at x is equal to 0.5. so if we write a command, see here float, since it is a real number, float substitute command, okay, in sort solution 1 x is equal to solution 1, okay, 0.5 for x, 0.5 for x in solution 1, we get the solution is what? 1.1331. Here you can also say this is what an exact answer, 1.31311. so this is what exact answer, and this is what an approximate answer. In maxima also we obtain an exact answer by using inbuilt function, and here this answer we obtain by using Euler method. So hope you understood this.